in this unit, we're going to focus on another type of addition reaction where we look at adding water and a halogen, X2, meaning Cl2 or Br2 typically, to an alkene molecule. This is going to be another example of the type of reaction where we look at, to start with, a carbon-carbon double bond, and during the course of the reaction, we're going to be adding two groups, in this case a hydroxy group and a halogen, across the carbon-carbon double bond. The type of product that results from this reaction is referred to as a vicinal halohydrin. The term vicinal is a general term that refers to two groups that are on adjacent carbons. So in this case, with our vicinal halohydrin, we have our carbon here and here. The chlorine and the hydroxy group are on adjacent carbons, and therefore we'd say the chlorine and hydroxy group are vicinal to one another. They are on adjacent carbon atoms. And then the term halohydrin, we can dissect the term halo, meaning halogen, and the term hydrin, meaning the hydroxy group there. So a halohydrin is a molecule that has a halogen and a hydroxy group on adjacent carbon atoms. And vicinal halohydrins are going to be the product that we get by reacting water and chlorine or bromine with an alkene. So let's go ahead and take a closer look at this reaction type. We'll begin with an example problem. So what we see in this example is we start with an alkene reacting with bromine and water. When we have a mixture of bromine, so with this reaction, you may draw some parallels between this and reactions that we've seen before, because previously we have seen reactions that had just an alkene plus bromine, and we have seen reactions that had an alkene plus water, and in the case of water, there was also an acid catalyst present. So what's going to happen if we take bromine and water and mix those both together with an alkene is, first off, due to the weakness of the bond between the two bromine atoms, we're going to have an attack of the pi electrons on one of those two bromine atoms, identical to the first step of the halogenation reaction where we were reacting an alkene with just bromine or chlorine in the absence of water. So first step of the mechanism for this reaction to walk us toward the product is going to be that the alkene pi electrons come over, form a bond to the bromine as the bond between the two bromine atoms breaks. So we can describe this first step as the pi electrons come over and attack the Br2. So we'll go ahead and draw out our starting structure, draw out our bromine, our Br2 that is, and remembering that that bond between the two bromine atoms is relatively weak and easily broken, we'll bring the pi electrons over. They attack that bromine there. The bond between the two bromine atoms breaks to release Br minus, and we'll go ahead and write out the intermediates that result from this step. So this is going to leave us with bromide anion, as well as our carbocation intermediate. So we've taken those pi electrons, we have a CH2 group on the end here, and we want to decide which of those carbon atoms is going to pick up the bromine. We want to make the most stable carbocation possible, and that's going to correspond to putting the bromine here on the end, because that would allow us to generate a secondary carbocation instead of a primary carbocation. So we'll go ahead and do that. And then with this, keep in mind that anytime we have an atom that has lone pair electrons on the carbon adjacent to the carbocation, we can make that three-membered bridge structure through resonance. And so we're going to do that instead of trying to do a carbocation rearrangement. So analogously to the reaction where we were adding a halogen across the carbon-carbon double bond in the absence of water, similarly here, we're going to make that three-membered ring bridge structure intermediate as one of our resonance forms. So no carbocation rearrangement will take place ever in this particular reaction mechanism, because instead the stabilization comes via resonance. So we'll go ahead and do our resonance stabilization. Still have two sets of lone pair electrons in that bromine, and now two covalent bonds, so it's going to have a +1 formal charge, and this is our intermediate hybrid structure. So keep in mind that the actual structure of the intermediate is a weighted average of these two resonance structures right there. So now we'll go on to the next step of the mechanism to take a look at what's going to happen and making our way toward the final product. So now what we're going to do that will distinguish this mechanism from the reaction mechanism where we had just bromine or chlorine and alkene in the reaction mixture is that due to the fact that we have water present, water is going to be able to come in and act as our nucleophile here, and it's going to attack the most electrophilic carbon atoms. So as we look at our structures up top here, we have 2 carbon atoms that are electrophilic there and there, or here and here. The one that's going to be more electrophilic is going to be the one on the right because that's the one that has a positive formal charge in one of those 2 major resonance structures that we've drawn there. And so therefore that's going to be the carbon atom that we want to attack, is that carbon atom on the right. It's going to be attacked by the lone pair electrons from the oxygen. So let's go ahead and draw that out. So what I've done is just redrawn the 3-membered ring structure, which by the way, there is a term we could use to describe that 3-membered ring. We refer to it as a halonium. The IUM there, much like ammonium, indicates that there's a positive formal charge, and that positive formal charge is on the halogen. So this would be described as our halonium ion intermediate. And the halonium is our intermediate here. And we're going to bring our oxygen atom over, acting as the nucleophile, attacking the electrophilic carbon right there. That forces the carbon-bromine bond to break and will give us our next intermediate. So to help me in drawing everything out and getting things in the right position, I've numbered the carbons of the longest chain in our intermediate. And I'm just going to draw now a 4-carbon chain here. And I'm going to number that 1, 2, 3, 4, and plug my groups onto the appropriate atoms. So at carbon 1, that's where we should see a bromine bonded because our carbon-bromine bond right here has not broken. It's still there, so I'm going to go ahead and plug that in. Put my Br onto the end of it. That bromine is going to have 3 sets of lone pairs because it had 2 to start with, and then we broke the carbon-bromine bond right there that I'm showing in green. And those electrons went onto the bromine. So we're good with carbon number 1, and that carbon number 1 would have a complete octet. We come over to carbon number 2, and carbon number 2 is where we had the water attack. So at carbon number 2, we need to make a bond that goes to H2O. So I'll go ahead and do that, also color coding it. Still 1 pair of lone pair electrons there that are free on the oxygen. And then carbon number 3 is where we see in the original structure that we had 2 methyl groups bonded. Those still need to be there, so I'll go ahead and plug those in, methyl and methyl, and then carbon number 4, and we've already included that. So that's our intermediate that we get by using our water to act as the nucleophile and attacking the most electrophilic carbon from our ring. So now onward to step 3, which is our final step of this mechanism. And the final step of the mechanism is that ultimately we want to generate a final organic product that has no formal charges. And so in order to get from our intermediate that we finished up with in step 2 to our final product, we just need to deprotonate. We need to remove a proton from our water molecule there that's part of our intermediate. So what we'll do here is a deprotonation step. Remember that when we say deprotonation, we're generally referring to that with respect to the organic molecule. So we're deprotonating the organic compound here. So let's go ahead and show that happening. So I'm just going to redraw our intermediate that we finished up step 2 with, and we'll deprotonate it. So I've redrawn the intermediate from the earlier step, and we're going to bring in a base, which we have water in the reaction mixture, so we can certainly use that as our base. Anything that's a lone pair of electrons here is certainly capable of acting as a base to grab that proton. That makes the oxygen-hydrogen bond break and is going to give us our final halohydrin product. So we'll go ahead and draw out our halohydrin product. And a good thing to check for here is definitely to make sure that this is a vicinal halohydrin. This reaction will always yield a vicinal halohydrin. And so you want to make sure that you do indeed, if you're on the right track with this, have the hydroxy group and the halogen ending up on adjacent carbons. If not, you've done something wrong along the way. So this wraps up our mechanism for this particular reaction. With this reaction, you will notice that our final product here has 1 chiral center. So we do need to consider the stereoselectivity of this reaction. And when we're looking at the stereoselectivity of this particular reaction with our acyclic molecule that we started with here, what will happen is that we'll end up with a mixture of R and S enantiomers, R and S chiral centers at that particular location. So if you're asked to show the stereochemistry of the major organic product here, we need to show both a wedge and a dash for that hydroxy group. So we'll go ahead and draw that. So in order to show the stereochemistry, what I did was just redrew the structures as planar structures, and I'm going to convert that line into a dash to the hydroxy group and a wedge to the hydroxy group to show the two different enantiomeric products. If the carbon that has the bromine bonded to it was a chiral center as well, right here, then you would expect that to also appear as both the wedge and the dash form. So now what we're going to do is move on to the issue of regioselectivity for this reaction. So for this reaction, the one that we've just looked at here, would we describe the reaction as regioselective? In other words, is there a preference for making a certain constitutional isomer over other possibilities? And the answer to that question is yes. There's definitely a preference that the OH group goes on the more substituted carbon, the bromine or other halogen goes on the less substituted carbon. So that is the regioselectivity of this reaction, and we can go ahead and write that down in words as a generic description of this reaction is that if we have unequally substituted carbon atoms, the bromine or chlorine goes on the less substituted carbon, the hydroxy group goes on the more substituted carbon. Remember, more substituted means the carbon that has more alkyl groups directly bonded to it. So I'll go ahead and write that rule out for you. So the reaction is regioselective there in the upper right corner with the hydroxy group bonding to the more alkyl substituted carbon and the halogen bonding to the less alkyl substituted carbon. We see that happening down here. The bromine is bonded to a primary carbon, the hydroxy group is bonded to a secondary carbon. That's always going to be the case. This is the way the regioselectivity works out due to the mechanism here that the first thing that happens is that the bromine comes in, or the chlorine, and the second thing is that the alcohol group forms. So now let's take a look at this reaction type in the case of molecules that have an alkene group within the ring, because this is going to introduce some additional interesting stereochemistry constraints, and we'll see some parallels here to the stereochemistry constraints that we looked at when we were doing reactions with just chlorine or bromine plus an alkene. So let's do an example problem here to illustrate the stereochemistry constraints that result from dealing with molecules where we have a ring. So we have our alkene starting material, our 5-membered ring called 1-methyl-1-cyclopentene, and we're reacting with chlorine and water. So when we see that mixture of chlorine and water, what we expect is that we're going to get a product that is a vicinal halohydrin, and we would be putting the OH group on the more substituted carbon, chlorine on the less substituted carbon. We need to look at the stereochemistry that's going to go on here as well. So in order to do that, I'm going to quickly go through the mechanism for this reaction, just like we did up top for the acyclic molecules. We're going to start by taking our pi electrons, having those come over and attack the chlorine atom, because that bond between the two chlorine atoms is relatively weak and prone to breakage. So it's going to be attacked by the pi bond coming over, forming a bond to one of those two chlorines. The other one breaks away to give us chloride anion, as well as our resonance stabilized carbocation intermediate. So we'll go ahead and draw out our 5-membered ring, and I'm going to make the more stable situation here, which would be bonding the chlorine right here to allow us to have a tertiary carbocation intermediate right there. And now that we've created that, we can show the resonance stabilization of that intermediate, which I'll go ahead and show as a green arrow here, electron pushing arrow, indicating that those electrons from the chlorine can come over, form a bond to that carbon to create a 3-membered ring as one of the resonance type structures here. So we'll go to make our 5-membered ring. We have a methyl group hanging off there, and then we have 2 bonds to chlorine there, and that's going to give us a positive formal charge and allow us to generate this so-called halonium ion, because we have a positively charged chlorine that's part of that 3-membered ring. Now, just as we saw in earlier mechanisms where we were working with a cyclic alkene reacting with just chlorine or just bromine, in order for this structure to be possible, both of these bonds to chlorine have to be in the same face of the molecule. They can't be one as a wedge, one as a dash, in other words, because that would cause one of those bond lengths to have to be way longer than is feasible. So those two bonds have to be cis to one another, in other words. And there's two ways to draw those bonds cis to one another. One is to have them both pointed toward you, which is what I'm drawing at this moment. The other is to have them both pointed away from you as dashes, which I drew there on the left. So we'll go ahead and fill in the full tetrahedron for both of these structures. And the fact that those two bonds to chlorine have to be in the same face of the molecule is going to introduce some stereochemistry constraints in terms of where the water is able to attack at this next step of the mechanism. So I'm showing the next step of the mechanism with a single-headed arrow indicating we're headed to the next intermediate. And the next intermediate corresponds to having water, H2O, come in and attack at the more substituted carbon atom, because the more substituted carbon is going to be the one that has the stronger carbocation character. Because when we looked at the major resonance structures, that's the one that has the positive formal charge in one of the resonance structures. So the lone pair of electrons comes in from the oxygen, attacks the more substituted of the two carbons right there. That forces the carbon-chlorine bond to break. And remember that for this water attack to be feasible, the water has to attack from the side opposite where the chlorine bond is breaking. So since the chlorine's aimed toward the back of the molecule, that means the water has to attack from the front side of the molecule, and therefore the water is going to end up on a wedge because a wedge faces forward. So this is going to be an attack from the front here, and the outcome of this is going to be that the water and the chlorine are going to end up on opposite faces of the molecule, because you see here that we have that remaining bond there to chlorine that is a dash, and the hydroxy group is going to be coming in as a wedge. So the other scenario is that, coming to this stereochemistry on the right, we could have the water attacking again here. And in this case that I'm drawing on the right-hand side, the water has to attack from the back because the chlorine is already aimed toward the front as wedges. So it's going to be a backside attack here. Carbon-chlorine bond breaks, like so, leading us to a couple of different intermediates in this stereoselective reaction. It's stereoselective because of the fact that the water has to attack from the front due to the fact that those two bonds to chlorine have to be oriented in the same face of the molecule, and the preferred conformation of the cyclopentane ring is going to anchor the molecule in place there kind of through that carbon-carbon bond that we have highlighted. Okay, so let's go ahead and draw the intermediates that would result from this step of the reaction mechanism. So our halonium intermediate on the left had the chlorine as a dash, so I'm going to put the chlorine as a dash here. And it has to have the hydroxy group showing up as a wedge because the hydroxy group, or more specifically the water, has to come in from the side opposite where the chlorine is. So that water is going to have a positive formal charge at this point, and the attack of the water is going to force that methyl group to be oriented now toward the back. The other intermediate stereochemistry that we need to go ahead and draw out here is going to correspond to also another example, another structure that is anti-addition, where instead we're going to have the chlorine oriented forward and the hydroxy group has to attack from the back. So we'll draw the hydroxy group, the water attack rather, from the back as a dash, and then a wedge now going to the methyl group. So these are going to be our two stereoisomer intermediates. And then once we deprotonate those, following deprotonation, we're going to end up with our final product having those two groups still trans to one another. So I'm just going to write deprotonation here. You saw the deprotonation step occurring in the earlier example. The same sort of process is going to go on here, that you just have water or some other base come in, grab a proton from the H2O to leave us with OH. So we'll go ahead and draw everything out here to give us OH that is trans to the chlorine. So in other words, we describe this as an anti-addition because the two groups that are newly adding to the molecule are adding in trans to one another. we go like that, and like so. And we could also describe these two structures that we've drawn here as a racemic mixture. That means that the two structures are related as enantiomers, and we expect there to be an equal quantity of each of those two structures form as a result of this reaction. So this is going to demonstrate, to go ahead and put this into words, we would describe the addition of H2O plus halogen as an anti-addition, because the two groups that are adding from opposite faces of the molecule. That's what causes this to be referred to as anti. So in other words, X and OH are going to end up trans to one another. So that's what you have to keep your eyes peeled for, is that those two are going to end up trans. And again, we've illustrated here that the OH goes on the more substituted carbon, Cl goes on the less substituted carbon. So if you were asked to go through and predict the major product of this reaction and you didn't want to draw out all the steps of the mechanism, you could just skip straight to the chase and plug in the OH and the Cl in the proper location, meaning plug the Cl onto the less substituted carbon, OH onto the more substituted carbon, and make those two groups trans to one another, and you'd be all set here. So with that, we conclude our discussion of adding a halogen and water to give this so-called halohydrin product that we've shown here